Beginning the last class, we were discussing a little bit of photogrammetric survey, aerial photogrammetry, etc. We saw the basic concepts. Okay, what is terrestrial photogrammetry? What is aerial photogrammetry? And then we went on to discuss about the basic terminologies. What is a principal point? What is tilt, etc. Right. Now we have few numericals to discuss. Before the numericals, the concept used in the numerical. So here what we are doing, we are finding out the scale of vertical photograph. So vertical photograph means it is taken without any tilt, right? Remember tilt when it was the optical axis was tilted by some angle, right? And when that tilt, there is no tilt, then it will be vertical photograph. So we need to see what is the scale of a vertical photograph. Scale, we already know by definition it is what? It is the map distance divided by the original distance. So if we have an arrangement like this, okay, so from the O, we are taking the pictures from the O point. Here at this distance of F, which is the focal length, the photograph is being generated. And these are the ground point, capital K, capital A, that is the ground point, and when it is A naught, that is data, that is the mean sea level. So what will be the distance of this line? Say for example, capital A, capital K, capital A, right? This is the distance of the line at the ground. Now this small k, small a is the distance of that same line in the photograph, right? So it's like this. We have the camera at O point is at certain height from the ground. This is the ground. And we are saying, okay, this is the data. So we are saying this is small h. What is this? This is the RL of the ground point. And we are saying that this is total is capital H. What is this? This is the RL of the exposure point or the camera from where we are taking the pictures. So this value, this much will be capital H minus small h, right? Now if we are taking a photograph somewhere and say we have, so this length, let's say this is capital K, this is capital A. So this length, if this is your focal, so the photograph will be generated somewhere here. So this will be the length of the same point in the photograph, small k, small a, right? Now what is the scale? Scale by definition is the distance in the map or in the photo divided by the original distance, right? So small a divided by capital K, capital A. This is going to be the scale of the photograph. Now, in this case, this is one triangle and this is another triangle. And from the principles of similar triangle, what we can write that F divided by this entire one of the bigger triangle, and this is equal to this one, small k a by capital K A, right? So we can write this from the principle of similar triangle, and we see that this is the scale of the photograph. So very easily the scale of the photograph comes up. Scale of the photograph is F divided by, so this is H. Capital H minus small h. What is F? F is the focal length of the instrument or camera that we are using. What is capital H? capital H is the RL or elevation from the datum from this point, exposure point, from where we are taking the survey, from where we are taking the pictures. And what is small h? Small h is the RL of this ground point. Okay, so that is what we are doing here. Here we have F, and this is O point. RL of the O point is capital H, we are saying. RL of the ground point, we are saying small h. So this is going to be the elevation of the exposure point from the ground will be capital H minus small h. And if we use the principle of similar triangle, we see that the scale is coming up like this: F divided by capital H minus small h. F is the focal length of the camera or instrument. Capital H is the RL of the exposure point. Small h is the RL of the ground point. So capital H minus small h is going to be the difference or the distance from the ground to the camera point, right? So this is very easy. So we have to remember this, and we will be using it in numerical. Then there is one small concept, relief displacement. Now, what is relief displacement? We see here, so take this for an example. There is a tower A naught, and we are taking pictures of this tower. We have a vertical photograph like here. So what will happen? This capital A point in the photograph is the small a point. And similarly, this A naught point, this is going to be this small a naught point. It is how the photograph will be taken, because this is not exactly um, below this photograph, right? There is an angle from the nadir point, right? Therefore, this is not going to be exactly below, even though this capital A point and capital A naught point, these 2 points are on the same vertical line. In the photograph, we will not see them in the same vertical line, right? There will be a displacement of their positions. So this is relief displacement. Okay, when the true position of the ground points are displaced in the photographs taken, there is relief displacement. Now we have to find out what is the relief displacement. Now, in this case also, we can use the concept of similar triangle. So we have a triangle, this O. Here let's put a small k point, O, small k, and A. We have one triangle which is corresponding to this O, capital K, capital A point. Then we have O, K here, and A naught, this triangle, and we have this triangle. So with this was our camera point. We are taking pictures of a tower, say for example, this is a point, this A naught is in the ground. So the photographs will be generated at the focal length, the distance of the focus. So this is going to be our A point. This is going to be our A naught point. So even though these capital A and A naught are in the same vertical line in reality in the ground, in the photograph we don't see them in the same position. There is a displacement. So this displacement is relief displacement. Okay. Now we have to find out what is this value. What we can do, we can use again the similar concepts of similar triangle. So here we have one triangle here, and corresponding here we have another triangle, right? And we can use this triangle here. Right? One triangle can be here, and corresponding triangle will be this one. corresponding similar triangle will be this one, right? So like this, we can use the concept of similar triangle and we can find out what is going to be the relief displacement. So if we go back here, so what we are doing, here we have f divided by capital H minus small h, this value, right? And we are saying these are r and r naught. Let's go back here. So let's say if this distance is r, then this distance and this distance here, they are same, right? They are both are r. So this is O point, this is small k point, this is capital K point, this is A1 point. Like this. So this is F, and we are saying this is R, and we are saying that, sorry, this is R naught, and we are saying this is R, like this. So we are using this triangle, and we are using this triangle. Okay. So if we go back here, what we see F divided by capital H minus small h. F divided by capital H minus small h. This will be corresponding to what? This will be corresponding to this R divided by capital R. Small r divided by capital R. From there, we can find R. We can find R. So what we need actually, we need the displacement between A to A naught. That is the relief displacement. From this value, the position has been changed. So what we are trying to find out, we are trying to find out is small r and small r naught. There we can find using the principles of similar triangle. Then finally, we will write r minus r naught. That will give us the relief displacement. So from this first triangle, we got this value. Then we go to the second triangle. We see that again f divided by capital H now. Now we are using this triangle, right? So f divided by capital H. Now this will be r naught here, okay? And r, capital R is same in both cases. So now it will be r naught divided by capital R. So from there we got the value of r naught. So we got the value of small r, we got the value of r naught. Now we have to find relief displacement. What is relief displacement? Difference between these two values, r minus r naught. So if we do this and we simplify a little bit, then finally this one is coming. So this is relief displacement. Now again, from the first equation, what we can write, we have this equation, we can write capital R is equal to this much, right? From this equation number 1, we can rewrite it this way. Why we are rewriting it this way? Because few of the terms will get cancelled. And from the equation number 2, we can rewrite it in this way. So we can either use equation number 1 here, replace it, or equation number 2 here, replace it. Then we will get this type of value. So if we do it equation number 1, this is what we are getting from equation number 1, the value of R. And the rest of the quantity is here. So we will multiply it. So we are finally getting a value small r, small h divided by capital H. Okay. Or if we use the equation number 2, we can get this data. So these two ways will give us the relief displacement. Right? Then we have one or two numericals based on this concept. The first one here, let's say, We have a vertical photograph taken at an altitude of 1200 meter above the mean sea level. That means it is the RL of that point, right? Determine the scale of the photograph for terrain lying at elevations of 80 meter and 300 meter. So in one case, RL of the ground is 80 meter, and another case, RL of the ground is 300 meter. So we have two cases. And when the RL of the ground will be changing, the scale will also be changing. So what will happen? Focal length is given. We have to find out the scale. So we know the formula. We have to remember the formula. We derived, or if you don't remember, you can quickly derive also, right? So using that same formula, what are the givens? Focal length is given. Elevation of the camera, RL of the camera point is given. Exposure point is given. And elevation of ground is also given. So 15 centimeter divided by 1200 minus 80 meter. Then we do the correction for their meter, centimeter, etc. So that they are in the same unit, and we got the scale of the photograph, which is taken at an elevation of 80 meter. For the one which is a 300 meter, focal length is same because the same instrument is being used, and elevation of the camera point is again same, but elevation of ground point is changing. So only this 300 is going to change. Only this 300 is going to change, and other things remaining same. We will do the correction for centimeter, centimeter by multiplying the meter with 100, right? And then we got the scale here. So these are the two scales. One scale is for elevation of the ground point at 80 meter, one scale for elevation of the ground point at 300 meter. Right? Very easy. Then there is another question. Here what we have to do, let's see the question. A line 2350 meter long, it is lying at an elevation of 500 meter. So length of the line is given, or distance between 2 points, okay, in the ground it is given. Elevation of that ground is given. The RL of the ground point is given. It measures 10.50 centimeter on a vertical photograph. So the distance between those 2 points in the photograph is 10.50 centimeter. The focal length of the camera is given, and we have to determine the scale of the photograph for an area having an elevation 1200 meter. Okay. So this is for a different case. The question that is asking us, we have to determine the scale of the photograph for an elevation of 1200 meters. So this is the second case. There are two cases. First, using the first conditions, we have to find out the values here. What is the elevation of the camera that is not given to us? There we have to find out. After finding out the elevation of the camera point, we can go on to find out this scale at the different RL of the ground, right? So we have the same formula. The values that are given to us, f, focal length is given. Capital H, we do not know. Small h, RL of the ground is 500 meter given. And scale, how can we find the scale? That is given that the original distance in the ground is 2350 meter, and the distance in the photograph is 10.50 centimeters. So that is given. So from there we can find out what is the scale. So scale at 500 meter elevation will be map distance by actual distance, right? So here we are replacing on the left hand side by the formula for the scale. We are writing the same thing on the other side. So 20 centimeter, capital H, and 500 meter. From here, we shall find out what is capital H. What is the RL of the exposure point? Okay. So we do some mathematics and simplification, and we got what is the value of the capital H. After getting the value of the capital H, now we can find out scale of the photograph at the elevation this much, which is asked in the question. So now this would be 1200, okay. So 1200 meter, the scale at that point will be again the same formula, f divided by capital H minus small h. Capital H we just got from the first condition. Other values are given, and we'll find out what is the scale in the 1200 meter elevation, right? Then now After this, we have to another small concept, ground coordinates. Okay, just like in the photograph, we can assign some coordinates. In the ground also, there can be some coordinates. And with these coordinates, we can find out what is the distance between 2 points. Okay, any 2 points in the photograph. And then we can correspond uh, that distance between 2 points in the photograph to the original distance, right? That way we can find out what is the actual distance in the field. So if we assign coordinates in the image small x, small y, and in the real ground capital X, capital Y, what will happen? Same thing, right? Same thing. If the small x is the coordinate in the photograph, that is the distance in the photograph, and capital X is the distance in the ground. So small x by capital X is nothing but the scale of the photograph. So from there, we can relate the capital X to the small x. The x coordinate in the ground is related to the x coordinate in the photograph with the help of the scale. Similarly, small y, that is the map distance or photograph distance in y direction, divided by capital Y, that is the actual distance in the ground, is nothing but the scale of the photograph, f divided by capital H minus small h, that way. Now, you have all the coordinates, capital XA, if you write for A point, okay, this is the same formula that capital XA is the ground coordinate for the A point, small xa is the coordinate in the photograph, right? That way we can have coordinates of A point, B point, C point, any point can have coordinates in this way. Now we have a very basic formula that we already know to find out the distance between any 2 points. So this AB distance will be given by this formula, right? Root over capital XA minus capital XB whole square, capital YA minus capital YB, right? That formula will give us the distance between any 2 points. Now to find out this, if we are given the coordinates of the photograph, we can use the scale formula and then we can relate the ground coordinate with the photograph coordinate. And then we can find out the distance between any 2 points. Right? Very simple. So we are just saying that there is some origin in the ground and in the photograph. So we are saying this is for A point, this is XA, sorry, this is YA, this is XA, right? For any B point, we are saying this is XB and this is YB. Now we need to find out what is this distance. So for that we have the formula, right? And these values can be found from the photograph coordinates. If the photograph coordinates are given, so if we write capital X by small x, this is what? This is map distance or photo distance to the original distance. So this is nothing but the scale of the photograph. So using this, we can relate the actual coordinate to the photograph coordinate. And then we can find out what is the distance between these 2 points. So if we go back here, what we are given here, there are 2 points, point A and point B. They are at different elevations. RL of point A is 650 meter and RL of point B 250 meter. They appear on a vertical photograph with a focal length 250 mm. Okay. And flying height is 2700 meter above the datum. That is the capital H. Now these are the photographic coordinates. So finally we need to find out what is the distance or length of the ground line AB. So what we will do, ground coordinates we shall determine with the help of photograph coordinates. We have capital H, we have small h, that is the elevation at A point, and we have also the focal length. So if we use those values, we are finding out what is the capital XA, what is the coordinate of XA, XB. Like this, we are finding out the coordinates, and then finally we use this simple formula to find out the distance between A and B, right? Okay, so that will be how for photogrammetric survey. Then uh, the last topic, very small topic, we have remote sensing. Now here we are using that same concept that we use in electronic distance measurement. What is that concept? Electronic wave, right? Electromagnetic spectrum. We are using that same electromagnetic spectrum in remote sensing as well. So there can be basically two type of remote sensing. One is active remote sensing and passive remote sensing. Active remote sensing is using active sensors. In active sensors, what they are doing, they have their own source of electromagnetic wave. And in passive sensors, they are using other electromagnetic wave, okay, by other sources. One common example will be the uh, visible light, right? The sunlight emitted by the sun, that is being used by the passive sensors. So this is basic difference between active sensor and passive sensor. And what principle they are using? They are using the principle that when there will be some electromagnetic spectrum or electromagnetic wave sent to a particular location, that location will have some reflection, refraction, scattering, etc., depending upon the material that is there. Okay, the behavior will be different in rock, in soil, in water. The interaction of the electromagnetic spectrum, electromagnetic wave with the ground objects will be different for different objects. So based on that, we will be able to determine, okay, this place has rock, this place has some soft soil, here we have water, here we have dense forest. Like that, we will be able to distinguish different objects on the ground. So this is an image taken by LiDAR technology, which is light detection and ranging. Okay, so this is part of remote sensing. So here we can see the color coding. So there are different items, and according to that, the energy absorbed, energy reflected, these categories, these conditions will be different according to different material. Here also, right? So based on these, we will prepare maps. Okay. And based on this, we will know, okay, this area is having dense forest, this area is having water, this area is having this kind of, population, dense population, higher infrastructure. Like this, all these data can be accumulated, and a map or detailed planning can be done based on this data. So what are the applications? There are huge numbers of application of this method, remote sensing. What we can do weather forecasting, we can use land use mapping. Okay, what type of land use are there, like what is the population density, what is the infrastructure density, forest, everything we can find out using this method, right? So environmental study can be done, natural hazard study can be done, minerals, etc. are there or not, it can also be studied to some extent. Urban development, it is used for urban development planning, highway routes, railway network planning, from where to where connect, right? It can also give us contours, ideas of contours, so we can also plan for flood forecasting, etc. So all these things can be done depending upon the map we are producing. Okay, and we will produce different type of maps, but the same principle, the basic principle is same, which is remote sensing. We are using electromagnetic wave. The electromagnetic wave are sent from a sensor, and then the electromagnetic wave, depending upon the materials that are there on the ground or on the surface we are trying to examine, there will be different characteristics of reflection, refraction, absorption of the energy. And based on that, we shall determine the characteristics of the ground. So here we have few theories I have written. You can go through. Is electromagnetic spectrum we have already discussed. Okay. So what electromagnetic are wave are used for what type of instrument are also mentioned here. You can go through them. Then components of remote sensing. What will be different components in remote sensing? There will be a platform which is carrying the sensors. Okay. Then this is ground based. There can be airborne platform also, which is carrying the sensors. There can be satellites also. All right. Now, what are the sensors? Sensors are the devices that is receiving the electromagnetic radiation, and they are converting the signal, converting it into signals based on the pattern, based on the energy distribution pattern on the ground. Right? Okay. So based on that, we will prepare the maps, and based on the maps, we will have different types of use of the remote sensing methodology. But the basic point is same. We are using electromagnetic wave. We are using how the electromagnetic waves are reflected, refracted, or scattered according to the phenomena features on the ground. Based on that, we are preparing our map, and based on that, we are doing everything else. So that will be all from my side.